In this chapter, we're going to introduce everybody to the concepts of probability. Primarily, we're going to go through some counting statistics and counting methods for different types of probability questions. And we aren't going to be using computational methods. We're simply going to be introduced to these concepts so that we can apply them in the future. The goals of this chapter are to understand the concept of probability, as well as to apply frequentist approaches to probability questions. So we will be going through some basic definitions for probability, including events, sample space, going through differences between two different views of probability, the frequentist versus the Bayesian approaches to probability. We'll then go through some counting rules, how events are related to each other, and how that changes those probability rules that we have gone through, and then take a look at conditional probability and Bayes' theorem. So let's first start off with an overview of probability. We'll start off with events in sample space, and then basic probability rules. But first of all, we want to go through the origins of probability. The fact is, real life is very unpredictable in many cases because of incomplete knowledge, for example. Sometimes we may not know everything there is to know about a system, so therefore we have to make some assumptions and hopefully from that make a fairly accurate prediction. Real life is also unpredictable because of large numbers. When there's a large number of things, it becomes more difficult to predict the action of one within many. We also have to be aware that sometimes the system you're looking at is sensitive to initial conditions. So that means sometimes you may have two identical systems, but due to their interactions and due to their sensitivity to what they were exposed to at the beginning, they may evolve differently, and their characteristics may converge to become very similar at some point, or they may diverge to create some sort of chaos between the systems. So we also have to understand that in real life, initial conditions will cause a system to evolve in different ways that may or may not be predictable. And last but not least, in real life situations, most of the time we have open systems. Although as physicists, we do like to think of everything in an ideal fashion, sometimes a closed system is not a very realistic system. And so external factors can always change the behavior of the components that we're very used to being in a closed system. So that causes things to be even more unpredictable. So there is a need for us to determine how unpredictable things are and how reliable results are, and that's where we start with our discussions of probability. So with probability, we first have to define that word, and there are two different definitions for that word based on what your method is or your approach. So you'll most likely hear, even online or when you're reading books, that there are two approaches to probability. There's the frequentist approach and there's the Bayesian approach. The Bayesian approach is very frequently used in statistics, so that's the one that we're going to focus on, especially near the latter half of the course. But let's start off with frequency, or the frequentist approach. If you're a frequentist, it means that you're going to care more about the frequency with which unpredictable events occur. So basically, you're looking at heads or tails for a coin flip. If it's heads, then there's a 100% chance that it's definitely heads and a 0% chance that it's tails. You're more worried about whether this happens or not. If you're looking at the probability from a Bayesian approach, then you're looking at the degree of belief that some hypothesis is correct. So when you look at the coin toss event again, and whether you're flipping for heads or tails, you're looking at how much do I believe it's going to be heads or tails? If I flip this, it's 50% chance that it'll be heads and 50% chance that it'll be tails. So that's where that approach differs. One is more worried about the actual data you're collecting and the quantity that you're recording, whether it's for sure heads or for sure tails. The other one is, let's make a prediction about how accurate our guess is going to be as to whether it's heads or tails. So the easiest way to differentiate between the two is one has to do with frequency only, the other one has to do with the degree of belief, and that is why the Bayesian approach is much more suitable for hypothesis testing. Because we have a hypothesis and we want to see how much it is trustworthy at the end of our analysis. So this creates two branches of probability that we will discuss. And so I went through how we can differentiate between the two methods already. I now want to go through events and sample space and just go straight into some counting principles for probability. So first, let's define what an experiment is. So continuing on with that coin flip example, we're going to call the outcome a simple event. So the experiment is me flipping a coin, and outcome is called a simple event. The possible outcomes are heads and tails. So when you're talking about a sample space, S, then S is going to be either heads or tails, but the sample space has a size of 2, where you list your the number of simple events that you have. So just be careful with the wording here. If you're asked about what the sample space is, you should list the actual names of the outcomes. If you're asked about how many possible simple events there are, then you can choose to list them if you want, or just present a number saying there's 6 possible events, or in this case, 2 possible simple events that can take place. So let's say you have 300 simple events, or 300 possible outcomes. Sometimes you want to look at a subset of those outcomes. And in that case, you can call an event a collection of simple events. So A is an event where you can roll a die and get a value greater than 3. That includes several simple events like 4, 5, and 6. So it's a collection of simple events when you are talking about an event that takes place. If you have experiments with different stages, for example, let's go with 3 separate coin tosses, you can create a tree diagram to help visualize the sample space. So over here, I have a tree diagram. You start off here and you flip a coin, and you either get from your first toss heads or tails. From each of these, you can toss the coin a second time and get heads or tails, and then a third time to get heads or tails. So all of these branch out into the different possible simple events, and essentially you get 8 possible outcomes from this. So I can say, what is the event? How many simple events are in the event that your first coin toss is heads? In that case, you have 1, 2, 3, 4 simple events that are part of one main event where the first toss is heads. So just keep in mind the different terminology. A tree diagram really does help when you're trying to visualize things. Now, let's take a look at the basic idea behind probability. Our knowledge of relative frequency from the previous chapter comes in very handy because from a total of n events that we have, we can see how many times an event A takes place. So basically, divide the number of times that A takes place by the number of total events, and you get the relative frequency. But as your n approaches infinity, we're going to reach the total population, and we can now define relative frequency as the probability of an event A. So over here, I have the probability of event A is equal to the limit as n approaches infinity of frequency over n. We're going to say NA is the frequency of event A, and capital N to be the total number of events. In that case, your probability is then NA over N. So that's basic probability, as in if I roll a 6-sided die, then my sample space is going to be 1, 2, 3, 4, 5, 6, because there are 6 faces to that die, and those are the possible outcomes. But we also have an equal chance of rolling for any of those 6 faces. So if I'm trying to look for an event where I'm rolling 1, then the total number of possible events is 6, then I have 1 out of 6 chances of getting that 1. So what we'll notice is that as we run an experiment and roll the die many, many times, the more we roll the die, the closer we will get to this probability. So important points, much like relative frequency, every probability has to lie between 0 and 1. You can't have over 100% or less than 0% of getting some value. has to be between 0 and 100%. Apart from that, if you have all your experiments done and you add up all the different probabilities, at the very end, you should get 100% of all of the probabilities. So if you sum up all the probabilities for all the simple events in S, you should be able to get 1. And if not, then we know that something is missing in either in our problem or in our solution. So now let's start doing some calculations with probability. We're going to introduce counting rules, event relations, and conditional probability. The first one we want to start with is a basic counting rule. It's just called the MN counting rule, and there's an extended version as well. The MN rule for total number of simple events, that's one that we're going to use quite a bit just to figure out how many total number of events are possible given M and given N. So if we have one event with M possible outcomes and another event with N possible outcomes, we simply multiply them with each other to get the total number of events possible. So let's say 5 tickets are in a hat. You have to select 2 of them. How large is your sample space? Well, we have to figure out what events we have. We have to select 2 of them, so there are 2 events taking place, the first selection and the second selection. The first selection is going to give us 5 possibilities, so we're going to say M is equal to 5. After we take out 1 ticket, we're left with 4 tickets. So the second draw gives me 4 possibilities. So how many possible values are there? And what is my sample space for selecting tickets? It's going to be 5 times 4 gives me 20 simple events that are possible. And that gives me the total number of different draws that I can have. Now, the extended MN rule is as simple as what happens if I have a third event, a fourth event, or so on and so forth. All I have to do is continue multiplying. So when do we use this? We use this when there's more than 2 stages to an experiment, and we'll just use I to represent I number of stages. So the example I have here is there are 3 routes to get from city A to city B, 4 of them from city B to city C, and 3 of them from C to D. So if we're traveling from city A to city D, how many options are available for us to travel from A to D? So there are 3 stages here, from A to B, B to C, and C to D. And we simply just multiply the number of routes for each one to get the total number of possible combinations of routes to get to our destination. So N1 is equal to 3, N2 is equal to 4, N3 is equal to 3, and the total number of routes is going to be 3 times 4 times 3 is equal to 36. So when do we use this counting rule? We use it when we're trying to figure out how many outcomes are possible without worrying about orders or groups or specific combinations within a group. So the next part really has to do with what if we do care about those things. So if we do, then we have to take a look at permutations and combinations. So these refer to the different ways in which objects from a sample space can be selected to form subsets. So that's very important to remember. If you're trying to figure out just how many possibilities there are, use the MN rule. If you're trying to figure out how things can be grouped together, then we should probably look at permutations and combinations. So the first one I'll start with is an easier one. What happens if we really care about the order of our outcome? In that case, we use permutations. With permutations represented by P, we have P Kn is equal to n factorial. N factorial is the total number of ways to arrange an entire set of n distinct items. So if we take a look at our basic probability and our MN rule again, if we have n distinct items, then, or let's just say n equals to 5, then if I have my first event, I have 5 possibilities. In my second event, I've removed one of those possibilities, so I have 4 left. My third event, I remove 2 of them, so I have 3 left. So the total number of ways to arrange an entire set of n distinct items would simply be 5 times 4 times 3 times 2 times 1 times 0. And so we can just write that as n factorial for the total number of outcomes. Now we have the denominator being n minus k factorial. N is the number of distinct objects that we have, and k is if we take these objects k at a time. So in that case, we have to subtract it in order to figure out something to divide the total number of outcomes by. So essentially, we're trying to divide the total number of outcomes by the total number of ways we can take these objects. So an example is here. There are 50 tickets and 3 are drawn in a specific order. How many ordered sets of 3 are possible? So we have n equals 50 for the total number of distinct objects. That means we have n factorial, 50 factorial ways to arrange this entire set. But we want to choose 3 objects or 3 tickets from this entire selection. So then we figure out how many ways we can do that. We have to divide by 50 minus 3 or 47 factorial. That's going to give me the total ways that I can choose 3 tickets in a specific order. So at the end, you have 50 times 49 times 48 is equal to that number of ordered sets of 3. So why does this make sense? It makes sense because if I have 50 tickets, I'm going to draw one and I have 50 options to choose from. So I do have to keep that 50 there for the first one. After I draw the second one, I'm going to remove another option. So I have 49 options left. And then I take another one and I have 48 options left. This gives me a total of 50 times 49 times 48. And that gives me my 3 tickets drawn for in all different orders. Now, if the order of the group doesn't matter, things get a little bit more complicated. We should expect less ways of ordering. We should expect less ways of doing things. Because if I were to choose the 3 tickets from before, I can choose 2 of the same tickets if I wanted, but now the combinations do matter. I worry about the actual repeat of the values, and I don't worry about the order of the values. So when do we use this? We're trying to use this if we ask questions like, how many ways can I pick k distinct items from a group of n options in any order? So then we can divide the total permutations from here by however many redundancies we have. So the redundancies is represented by k factorial. So if I choose 3 tickets from a total of 50, then my redundancy is 3 because I'll get a whole bunch of different combinations with 3 repeats. So then we have to divide by k to get the total number of combinations possible. So another example, how many ways can I give 3 gifts to 8 people? I have a total of 8 people and I have 3 gifts that I can give, so k equals 3. So we have C, 3, 8 is equal to this, and we end up with 56 ways to give 3 gifts to 8 different people. Okay, so event relations, we're now talking about how events can be related to one another, and there are different ways of calculating probability. Now, the first one I want to go through is what happens if you have a union of events. A union of events means that you have your sample space over here in the box, and that's the same for each of these. And I have the rectangle being the sample space. I have my event A taking place here and event B taking place here, and there's some sort of overlap. Now, if there is overlap, we call this a union. And this means that either events A or B can take place. The only problem is if I want the chances or the probability of A or B taking place, I can't simply add these two up because there's overlap. I would be double counting the overlap. So I take the probability of A taking place, I add it to the probability of B taking place, and I have to subtract one of the probability that A intersects with B. So I have to remove one of these from the equation. So essentially what we're trying to calculate is one whole circle plus a portion of a circle. What else do we have? Sometimes you can have a disjoint or a mutually exclusive event. So that means that your union does not have an overlap. So these two circles are completely separated, and that means you can simply ignore this term over here, and you end up with the total probability being the probability of A plus the probability of B for either event taking place. The other two terms we want to learn about are intersection and complement. I'm going to start off with complement because that one's a little bit easier. If I have the probability of A, then the probability of the complement of A is going to be everything else. So AC is the complement of event A, and what it means is the probability of event A not taking place. So that's pretty much everything else in the sample space except for A. So in that case, you can easily calculate the probability of the complement by just subtracting the probability of your event A from a total of 1. Okay, now back to intersection. The intersection of A and B, represented by this symbol over here, the intersection symbol. It's like a downwards cup called a cap. This is when both events A and B, or A or B, can occur. In that case, you're going to have to multiply the probability of A by the probability of B, given that A occurs, which is also equal to the opposite. You can multiply the probability of B taking place by the probability of A taking place, given that B has taken place. So that means that you're only limited to this overlap in the middle, and that's what we're worried about when we talk about intersections. With these, we'll come up with equations to figure them out later on as well. So how do we calculate things with event relations? I have an example over here just so that I can walk you through it. Right here we have a question that says, after surveying 1,000 adults, the respondents were asked about their opinion of the expense of university education. Results are given in the probability table over here. Now, 3 questions. What's the probability that the respondent has a child in university, that the respondent doesn't have a child in university, and that the respondent has a child in university or thinks that the loan burden is too high? So let's take a look. The first question is the probability that the respondent has a child in university. Now, here's child in university, 0.35, 0.08, 0.01. We can add all of these together to get the total probability that a respondent has a child in university. So it's simple addition over here, and you get 0.44. The other thing you want to check is in the table itself, can you do simple calculations? If I add up 1, 2, 3, 4, all 6 of these options, I should get 100%. So you can try that out. You do get 100% here. So that means that we're safe to assume that the entire data set is complete. Sometimes you do end up with probability tables that do not present all the probability. So let's say this was 0.05 instead. That means there's going to be 0.15 missing. And that could be for people who didn't have an opinion. So it could be another category here, D, that was just no comment, but it wasn't useful to the conversation, so it was left out. But in this case, we don't have to worry about it. We can simply move forward with the calculations. Number 2, we want to see the probability that the respondent doesn't have a child in university. Once again, no child in university, simply add all these up and you get 0.56. Another way to do it is to use the result from the first question. We know that this is essentially a binomial experiment. There are only 2 options, either the child is in university or the child is not in university. So that means if I want to figure out the probability of E, I just do 1 minus the probability of D. So you end up getting the same answer. Third question, what is the probability that the respondent has a child in university, so has a child in university, or thinks that the loan burden is too high? So we're looking at this row and this column over here. And we're looking at the union of events. It's either or. So over here, I have the probability of A, like this, and then the probability of D. So probability of A for too high, which is 0.35 plus 0.25 to give 0.60, and the probability of D, which is all three of these, to give 0.44. But there is overlap between the two, so I have to subtract the intersection between the two. So the intersection is going to be child in university and too high, and it's 0.35. So I subtract that as the intersection, and I get 0.69 as my probability that the respondent either has a child in university or thinks that the loan burden is too high. So note that any combination of events from A, B, C, right here with D and E, they're not mutually exclusive. So we really have to be careful when applying the equation for unions, because it'll determine whether you need to subtract an intersection or not. That's the only thing to watch out for when you're doing these event relation calculations. Next, we want to take a look at conditional probabilities. A conditional probability refers to the likelihood of an event occurring based on the occurrence of a previous event. So prior, we did talk about intersections, and we did have an equation over here. Now we'll be able to define that equation. So usually we write a conditional probability with an absolute value sign or a vertical line. We have the probability of A given that B has taken place. And this can be defined in two ways. We can define it as the fraction of PB that intersects with A. So we have this, it's equal to the probability of A intersecting with B divided by the probability of B. But we also know that the probability of the intersection is given by this. So we can say, after combining everything together, that PAB is equal to PA times PBA divided by PB. And altogether, that's called Bayes' formula. Why is it Bayes' formula? And why did we suddenly introduce Bayesian statistics and probability into frequentist analysis? It's because we've now introduced givens. So these are conditional probabilities in which we are finding a probability given that something else has taken place. And so in that case, we can use that as part of Bayes' theorem. So this is the only equation that you would have to know about. And in terms of the types of problems you'll be presented with, you would be given these values. You would just have to know which ones to pick in order to calculate your probability. So last but not least, when we're going through these definitions, I do want to define what happens if you have an independent event. An event is called independent if and only if either of these conditions are satisfied. You either have the intersection of A and B being equal to the probability of A times the probability of B, or the probability of B given A is equal to the probability of B. If these are not satisfied, then your two events are considered dependent. And keep in mind, mutually exclusive and independent do not mean the same thing. So let's walk through an example together where we have to apply conditional probabilities to figure out, to calculate a probability. We have two cards that are drawn from a deck of 52 cards. We're now trying to calculate the probability that the draw includes an ace and a 10. So our event of interest is called A. We're just going to say A means we've drawn an ace and also a 10 with the two cards. The first thing we should understand is at the very end of this, we will be applying an intersection of events. So therefore, we have an intersection here. We can't get there, though, without doing some additional work. So first, we define what A is. A is going to be the union between B and C. But what is B and C? Let's first backtrack a little bit. If I draw an ace and a 10, there's two ways I can do it. I can draw an ace and a 10, or a 10 and an ace. So there's two possible ways of doing it, and that means there's two different events. So therefore, A is going to be the union of these two events. Either one can take place, so that's why that's a union. Then we have to further define what B and C are. B and C are mutually exclusive events, and they are defined as intersections of events with known probabilities. So B is going to be when you draw B1 and B2. So B1 is going to be the first draw being an ace, and B2 is going to be the second draw being a 10. So if both of these take place at the same time, then you have B, or the intersection of B1 and B2. Same thing with C. C is defined as the intersection of these two events, where C1 is drawing a 10 and C2 is drawing an ace. So we've fully defined this. Now we can apply the multiplication rule for conditional probability. We have B1 intersecting with B2 is equal to the probability of B1. And the probability of B1 is simply, so we have the first draw is an ace. There are 4 aces in a deck of cards, so we have 4 out of 52 chances of drawing an ace. Now that we've drawn an ace, that's already a given to us. We now want to see what the probability is of B2, which is drawing a 10, given that we've already drawn an ace. So given that we've already drawn an ace, it means that we only have 51 cards left, but we still have 4 10s in the set of 52. So the probability is 4 out of 51. The probability for C1 intersecting with C2 is exactly the same. There's no difference between the two. So based on that, we can now go back and try and figure out the probability of our main event A. So the main event A is going to be an addition. It's going to be the probability of B taking place plus the probability of C. And because they are mutually exclusive, that means that we can add them without subtracting the intersection. So we have the probability of B plus the probability of C. They're both the same. So we have 2 times the probability of B. Now, what is the probability of B? It's the same as this because we've defined it as so. So we just do 2 times 16 over 2,652, which is these two multiplied by each other, and we can simplify to 8 over 663. So just keep in mind when you are doing problems with this, make sure you explain your steps and thought process so that we can see where you're coming from. So let's do a quick summary. What should you have learned from this lesson? We should have learned the 2 different views of probability, the frequentist versus the Bayesian views of probability. You should understand how to determine sample sets, simple events, and total outcomes. You should be able to calculate basic probability in different cases using the MN multiplication rule or the extended one, permutations and combinations, and different event relations. And you should be able to apply Bayes' rule based on conditional probability. So those are the key things to remember and keep in mind before you move forward with the next chapter.